Hi everyone, my name is Euan McGill, and today I'm going to be discussing a probabilistic framework for assessing the impact of electric vehicles in low voltage distribution networks. I'm going to start today by providing a brief introduction to the topic, including the motivation behind the work. Next, I will present a high-level overview of the probabilistic framework, and this will include the stochastic and controlled inputs, as well as the measures of LV network performance. The results in this presentation are based on a single residential LV network, so I will also provide a description of the network topology. I will then provide a detailed example of how the probabilistic results are interpreted, and at this point we will consider only a single EV charging scenario. Building on this, a comparative assessment of multiple EV charging scenarios is then presented. I will then conclude with a summary of the key findings. Okay, so as you will most likely already be aware, the rate of EV uptake in New Zealand is accelerating. In fact, the EV fleet has doubled annually for the last 3 years, reaching around 14,000 by, as of April 2019. While this only represents around 0.35% of the national light vehicle fleet, the clustering effect can cause the effective penetration level within individual LV networks to be considerably higher than this, or will in the future. Load flow simulations allow future EV penetration levels to be assessed in advance. Yep. The probabilistic framework is based on an LV network and EV battery co-simulation. The simulation has a 1-week time horizon and uses half-hourly temporal resolution. Baseline load is modelled using smart metering data. And this data comes from the week which contains the annual peak that year. EV load is generated from the EV battery simulation. The simulation has stochastic inputs, and hence the week-long simulation is performed repetitively, producing statistical results. The stochastic inputs are necessary in order to capture uncertain elements within the modelling process. These include load sampling and placement, EV placement, EV arrival and departure times, and also EV distances travelled, which are used to calculate the individual EV energy requirements. The controlled inputs allow us to query the impact of certain parameters related to EV charging. These include the charger rating, range anxiety factor, and charging strategy. LV network performance is assessed via network voltages, conductor loading, and transformer loading. Throughout this presentation, the results are based on the network topology seen. I don't know if you can see that laser, but the network topology seen here. This was identified from previous green grid research and was chosen as it represents the most typical residential LV network. It has 71 connections in total. Okay, so now just a little bit more information on the stochastic inputs. A smart meter data set of over 2,000 properties was used for baseline load modelling. Anonymity requirements mean that smart meter locations are not known. Instead, loads are sampled at random. The distribution of annual energy consumption in the dataset can be seen to the distribution there on the right. And this demonstrates considerable variation in property sizes. Of course, for any given sample, there's also a greater number of unique load placements within the LV network, and hence load placement was another of our stochastic inputs. Similarly, EV placement can have a significant impact on load flow results, particularly at low penetration levels. For example, a higher number of EVs placed towards the end of the 2 radial feeders seen there is worse than if we had the EVs placed back up near the transformer. EV placement was hence another of the stochastic inputs. EV arrival and departure times are also sampled from distributions. Arrival times are assumed to be normally distributed around 6 p.m. and this can be seen in the blue distribution on the left. Similarly, departure times are normally distributed around 8 a.m., which is seen in the orange distribution there, again on the left. And both distributions have a standard deviation of 1 hour. These distributions were assumed in the absence of a kind of large enough body of perhaps trial data or survey data regarding when people arrive. So hopefully we can improve on this in the future. The daily distances travelled were sampled from the distribution on the right, which is based on data from the Ministry of Transport for all light passenger vehicles. So the upper tail of that distribution has been clipped in order to account for the maximum range of a typical EV. The controlled inputs allow different EV charging scenarios to be defined and then assessed. The controlled inputs are charger rating, range anxiety factor, and charging strategy. The charger rating is of course pretty self-explanatory. It's assumed that all EVs charge at the specified rate. The range anxiety factor allows us to model an EV owner's tendency to charge. So for example, will EV owners charge every night when they arrive home independent of their state of charge on arrival, or will they only charge when their arrival state of charge at night is insufficient to cope with their journey needs the following day? The charging strategy defines how EV load is scheduled subject to the relevant constraints. So as an example here, I've put in the on arrival strategy, which just simply means EVs begin charging as soon as they arrive home each day. As previously touched upon, the simulation has a time horizon of 1 week and half-hourly temporal resolution. This results in 336 time steps during the course of the week. For each time step, we record the minimum network voltage, maximum conductor loading, and also the transformer loading. At the end of the week, we then evaluate the absolute and 5% extreme values. Taking voltage as an example, since here it's under voltage which is of concern, these are the weekly minimum and 5th percentile voltages. After performing multiple iterations of the week-long simulation, we can then observe the distribution of these measures. Okay, so let's take a look at an example of some results. These results correspond to the charging scenario that was seen previously, and that was, just to reiterate that in case we forgot, that was a charger rating of 3.7 kilowatts, the range anxiety factor of 1, and using the on-arrival charging strategy. Here we can see the distribution of both the weekly minimum and weekly 5th percentile voltages as a function of EV penetration level. The weekly minimum voltages are those seen in blue, and the weekly 5th percentile voltages are those seen in red. For both the minimum and 5th percentiles, we can see a clear downwards trend with increasing penetration level. What we can also see at each penetration level is a significant variation in both the weekly minimum and 5th percentiles, and these are due to the stochastic inputs that we discussed previously. The dashed blue line indicates the 0.94 per unit threshold, and this corresponds to the lower limit of the New Zealand steady state voltage limits. I've also added a lower threshold in red, and this allows us to further assess the severity of any undervoltage events. One thing worth noting is the per unit scale on the y-axis there. We can see that for low penetration levels, there are some weekly voltages which are around the 0.99 per unit mark. This may seem a little bit bizarre. The reason for this is that the distribution transformer is assumed to provide the secondary voltage of 1.05 per unit. So 0.99 per unit still represents a semi-significant voltage drop. And as I understand it, this is typical of many LV distribution networks in New Zealand, that's to have the distribution transformer secondary set to 1.05 per unit. Okay, the probability of a single weekly voltage excursion beyond 0.94 per unit can be interpreted from the minimum weekly voltage distribution, as shown here as an example for the 75% penetration level. This provides a probability of around 95%. Similarly, the probability of a single weekly voltage excursion beyond 0.9 per unit can also be interpreted from the minimum weekly voltage distribution. This time, however, as shown here, and this provides a probability of around 25%. The probability of voltage excursions beyond 0.94 per unit during 5% of the time during a week can be interpreted from the weekly P5 voltage distribution, this time as shown here. And this provides a probability of around only 5%. So these results allow us to get a better understanding of both the severity and frequency of undervoltage events. It can be seen that as the EV penetration level increases, each of the aforementioned probabilities also increase, and some level of future discussion is required in order to better establish what would be appropriate planning levels for each of these different probabilities. The same approach is used to interpret the both transformer and conductor overload probabilities. What differs here is that we consider the weekly maximum and 95th percentile load values. Loads are expressed as a percentage of the rated value, and hence the overload probabilities can be interpreted as the percentage of the box plots above the 1 per unit threshold. Similarly, an extended upper threshold of 1.1 per unit was also included, and again, this allows us to better assess the severity of any overloading events. Again, at each penetration level, we can see considerable range, and again, that's due to the stochastic inputs that we discussed previously. The graphs to the right depict the transformer and conductor overload probabilities respectively, and again, both the severity and frequency are considered. Okay, so far we've seen that voltages, transformer loading, and conductor loading can vary significantly for successive repetitions, and this is due to the stochastic inputs which we sampled. We've also seen that the distribution of these measures allows us to interpret the constraint probability. What we do is we observe for convergence of these probabilities, and what this shows is that no additional number of repetitions will affect the simulation results. So what we can see here is what this graph shows is the probability of a single weekly voltage excursion beyond 0.94 per unit, and how this varies as a function of the number of simulation repetitions that were performed. The 5 trends there correspond to the 5 penetration levels that were examined. So we can see that whilst initially volatile over the first 100 repetitions, the results soon converge. By 1,000 repetitions, the results have converged to within 1%, and there's very little change observed over those next 1,000 iterations. And it's these converged results that we presented in the previous slides there, as we've demonstrated here. So that maps the converged results onto those bar charts that we've seen previously. Does that make sense? Okay, so now that we know how the probabilistic results are interpreted, we can now begin to look at a comparative assessment of different EV charging scenarios. As shown here, we're going to consider 3 different EV charging strategies, and these are the on-arrival, night tariff, and by morning strategies. In each case, I've kept the charger rating and ranging exactity factor equal in order to provide some consistency there. Okay, so with the on-arrival strategy, EVs begin charging as soon as they arrive home each day, the impact of which on transformer loading can be seen here. Shown is the daily load profile beginning at 1 p.m, and both the baseline and EV load at each penetration level are indicated. With the night tariff strategy, all EV charging is delayed until after the night tariff start time, 9 p.m. And with the by morning strategy, EVs begin charging overnight at the time required to be full by departure the following morning. As an example of the results, let's look at the probability of a single weekly voltage excursion beyond 0.94 per unit, and let's see how this varies for each of the charging scenarios we've previously described. We can see that the on-arrival charging strategy provides the worst performance. This is because As you would imagine, on-arrival charging compounds the baseline evening peak. The by-morning strategy provides the best performance, and while at lower penetration levels, the difference between the by-morning and night tariff is relatively small. As the EV penetration level increases, this difference becomes significant. And this is because with the night tariff strategy, EV load diversity is lost. So whereas before vehicles were arriving home at different times, people living different lifestyles, but if we're all responding to a single uniform time of use signal, then that's not particularly good, especially at high penetration levels. And what this results in is that we just then begin to see a new peak load occurring at 9 p.m. rather than earlier in the day. Due to variation in vehicle departure times in the morning, and also the arrival state of charge that they arrived home with the by-morning strategy, this natural diversity is maintained. So that's one of the things we can leverage just naturally in order to improve the performance of the network. Okay, so that's just about it from me. I'll just round things up with some quick conclusions. We've seen that while stochastic inputs are necessary in order to capture uncertain elements within modelling, they can significantly impact load flow results. Running only a small number of simulation repetitions can result in conclusions being drawn from statistical outliers. Running a larger number of repetitions produces a stable set of statistics. There we go. And from these statistics, we can interpret the probability of network constraints arising. And we've shown that by utilizing different EV charging strategies, we can reduce these constraint probabilities. We've also seen that both the frequency and severity of voltage violations are useful indicators. And this is something which is recognized by the European standards for voltage limits and perhaps may be worth considering in New Zealand rather than absolute measure. And yeah, finally, unlike with deterministic simulations, we cannot definitively say whether constraints will or will not arise at a given penetration level. And instead, we have to describe this via probabilistic measures. And therefore, future work will need to establish what appropriate planning levels would be for these constraint probabilities. Yeah, thanks for listening. Thanks to the sponsors. If you've got any questions, just give me a shout.